asistencia a este seminario internacional sobre diseño y análisis de experimentos para encuestas de diseño complejo. Este seminario será en inglés y simplemente le doy la palabra al doctor Enrique de Alba, quien nos dará un mensaje de bienvenida. Muchas gracias.
Sí, gracias, Ricardo. Buenos días a todas y a todos los asistentes a este seminario sobre diseño y análisis de experimentos para encuestas de diseño complejo. Un atento saludo de la doctora Márquez, quien iba a dar estas palabras y por cuestiones de agenda no pudo asistir. Pero a nombre de ella, bienvenidos a esta conferencia. Y ahora cambiaré al inglés, ya que nuestro conferencista es la lengua que usará. Good morning to you all attending this seminar on design and analysis of experience for complex design surveys. This is an effort of INEGI to develop answers and obtain solutions to questions that every National Statistical Office faces when changes to surveys are needed. What should we consider before introducing changes to the surveys? What are the parameters we should build and consider, mainly on the effects and consequences of introducing such changes? We have received messages from other Mexican public institutions and other national statistical office dealing with surveys saying that they share our worries and challenges and will be part of our attendees. So welcome to the seminar. Official statistics and statistics in general is all about producing and analyzing data in support of sound decision making. Statisticians have always been involved in the development of two important ways to produce useful information: experiments and surveys, and others. Accepting the need to introduce changes to improve our surveys, maintaining the quality and comparability of the information produced, institutions in charge of conducting surveys, as INEGI, require making decisions about the introduction of changes in parts of the surveys. Therefore, the seminar intends to review the experiences from other national statistical offices and academics, bringing some thoughts on the questions of introducing changes to surveys. We actually have been doing changes, but we don't have a protocol, criteria to do them. We do the changes, we analyze the results, we test whether they are significant, and see what decisions we take from them. But what we need is something more formal. The the dynamics of the subjects studied through surveys based on household samples, as well as the dynamic of the environment in which they are carried out, lead to the need for changes throughout the entire information production process. Changes considered as minor by those responsible for the survey lead to important variations at the time of the dissemination of the results. Thus, it is necessary to carry out pilot studies that allow the evaluation of the consequences of the methodological modifications. In the context of experimental sciences, theoretical and practical proposals have been developed to efficiently generate information that allows a systematical comparison among the obtained results under different situations in support of decision making. Therefore, Proposals aimed at incorporating the experience and learning of experimental science in decision-making have emerged regarding the introduction of changes in surveys whose samples are obtained through complex designs. The seminar on design and analysis of experiments for complex design surveys begins today with a keynote speech by Professor Jan van den Brakel, currently a lecturer of survey methodology at Maastricht University and senior statistician at Statistics Netherlands. I will now introduce the keynote speaker briefly. Jan van den Brakel is extraordinary professor of survey methodology at Maastricht University and works as senior statistician at the methodology department of Statistics Netherlands, CBS. He is involved in quantitative economics, econometrics, School of Business, and economics. He has a general interest in survey methodology. Among other topics, he works at sampling, weighting, variance estimation, design and analysis of experiments embedded in probability samples, inference with data obtained with mixed mode data collection, small area estimation, time series modeling of series observed through repeated surveys, inference for official statistics with data obtained without probability sampling. Jan van den Brakel have a useful papers about topic. I'd suggest has useful papers about the topic. I suggest to read all, but particularly quality procedures for survey transition experiments, time series and discontinuities, analysis of expense embedded in complex sampling designs, design-based analysis of embedded experiments with applications in the Dutch labor force survey, and design-based analysis of factorial designs in embedded improbability samples. I guess you could read anything related to the topic by Jan van den Brakel. He has an extensive literature, and without further ado, I give the floor to Jan, please.
Thank you. I will try to share my screen. So can you see my screen and the slides?
Yes.
Thank you. So thank you for the introduction. Thank you for the organizers of this nice seminar to invite me. And yes, let me start. The purpose of this paper is to present a design-based inference framework for the analysis of experiments embedded in probability samples. And the paper is outlined as follows. I will start with a brief introduction to explain what we mean with an embedded experiment. I will briefly say something about design issues if we want to embed an experiment in a probability sample. And then I will continue by introducing a design-based framework for the analysis of one-factor designs. I will extend it to factorial designs, highlight some special cases that shows the relation with the traditional model-based analysis methods from the theory of experimental design. And I hope that I have some time to illustrate it with an application and wrap up with a discussion. So starting with the introduction, this figure of this slide illustrates the idea of an embedded experiment. And it also explains the structure or the situation that we consider in this paper. So our starting point is a finite target population, all people living in Mexico. And from this target population, we draw a probability sample. And in this paper, we consider all possible general complex sample designs, which can be defined by its first and second order inclusion probabilities, pi I and pi ij. And then in the next step, the sample is randomly divided according to a randomized experiment into k subsamples. And we can do that according to a completely randomized design, a randomized block design, but also factorial designs, as we will see later on. And the sampling units that are assigned to one subsample are assigned to one particular treatment or survey implementation. So we have, for example, capital K different treatments that we want to explore. So we split the sample in k different subsamples, and each subsample is assigned to one of these treatments. And the purpose of such an experiment is to make estimates for the population parameter of interest under these different treatments or survey implementations, and to test hypotheses whether these sample estimates are significantly different from each other or not. So I already covered here the purpose. So again, we want to test, we want to estimate population parameters under different survey implementations and test hypotheses about possible differences between them. And this kind of experimental research finds applications in survey methodology and official statistics. For example, to improve the survey process of a repeated sample by testing the impact of different questionnaires or different data collection modes. Or more importantly, to detect and quantify discontinuities that are the result of implementing a whole new survey process in an ongoing survey. Or more generally, to quantify non-sampling error sources in survey research. Now, this is of course not my own idea. The literature to this kind of experimental research dates back to a paper from Maastricht from 1946. And he called it, but he introduced that under the name of interpenetrating subsampling. Also in the book of Cochrane on sampling theory, you find this kind of research under the name of split ballot designs. And Feinberg and Tanner has some early papers where they talk about this kind of designs, and they called it embedded experiments, and that is also the name I adopted here. Now, an advantage of embedding randomized experiments in a probability sample is that it potentially combines the strong external validity that comes from probability sampling, which means that it allows you to generalize results from a small sample to a large intended target population. Well, that can be combined with the strong internal validity that comes from randomized experiments, which means that experimental designs focus on guaranteeing the causality between the differences in the experiment with the observed different treatment effects that we observe in the experiment. Now, if we do this, if we design this kind of experiments, the question raises, should we apply a design-based mode of inference, which relies more on the theory of sampling theory, or should we use the traditional model-based inference methods as they come from the theory of randomized experiments? Now, the advantage of a design-based inference method is that it's more helpful to generalize results to a larger target population. And the position that we take in this paper is that we propose a design-based inference method in order to facilitate the generalization of the observed treatment effects in the experiment to a larger intended target population where the probability sample is drawn from. And we will do that for single factor experiments that will be designed, can be designed as completely randomized designs or randomized block designs, or we will also give the extension to factorial designs where we test more factors in one experiment. Now, a few words on designing such experiments. A few steps are highlighted here where you have to take a clear decision on. First step is to specify the type and number of treatment factors and the levels for each factor that have to be tested. And that naturally results in a clear specification of the hypothesis to be tested about the main effects of the different factors and also the interactions between them. Sorry. And we should also make a choice of a set of pre-specified set of target variables for which we want to test this hypothesis, just to avoid a necessary amount of post hoc analysis. And at the end of the day, these decisions should also result into a calculation of the minimum required sample size that is required to observe pre-specified treatment effects for these hypotheses at the pre-specified significance level and power level. Now, an important aspect is to choose an appropriate experimental design. The most straightforward way, once we have drawn a random sample from a target population, the most straightforward way to randomize the sampling units over the different treatments is to apply what is called a completely randomized design, which just implies that regardless the structure in your sample, you just randomize or allocate randomly the sampling units over the k different treatments of your experiment. That is a very simple approach and not necessarily the most efficient way to choose. One way to improve the precision and the power of your experiment is to apply what is called a randomized block design. That means that you do some kind of restricted randomization. Randomized block design refers to the concept that you first divide your sample in more or less homogeneous blocks or groups, which are called blocks in this context. And then you do the randomization of the sample units within each block independently. And that allows you in your analysis to remove the variance between these blocks from the variance of your estimated treatment effects. This is really similar to the concept of stratification as we know it from probability sampling. And typically, if you embed an experiment in a probability sample, the sampling frame of your probability sample gives you all kinds of ideas of potential block variables that can be used. Because we all know that sampling units that come from the same strata or the same cluster or the same primary sampling unit, or also respondents that are interviewed by the same interviewer, they tend to be more homogeneous than sampling units that come from different strata or different clusters or different primary sampling units, or respondents that are interviewed by different interviewers. So these kind of structures from your survey sample can be used as potential block variables in your experimental design if you want to design or set up an embedded experiment. Another thing to consider are factorial designs versus single factors. In a factorial design, you combine two or more factors in one experiment. If we, for example, one factor is, for example, 3 different versions of a questionnaire, and another factor would be 4 different versions of data collection modes. And if we want to test the effect on the outcomes of a survey, the first thought would probably be to conduct 2 separate single factor experiments, but it is more efficient to combine them in one experimental design where the levels of both factors are all cross-classified with each other, resulting in a full factorial design. And that is more efficient, that it requires less sampling units to test the main effects at the same precision, and it also allows you to analyze interactions between them. Another important aspect is to choose the level of randomization. From a statistical point of view, it is most efficient to choose the ultimate sampling units as the experimental units that are randomized over the different treatments. But as we will see, For practical reasons, it might be necessary also to choose clusters of sampling units. For example, the sampling units that belong to the same household, or the sampling units that belong to the same primary sampling unit, or the sampling units that are assigned to the same interviewer, to use these clusters of sampling units over the treatments at the cost of reduced power for variance estimation. Now, let's start with introducing our design-based analysis approach for a one-factor experiment at k levels. So again, our starting point is to select a generally complex sample from the target population. So we have a probability sample S of size n. And according to a factorial design, this sample is further split up in k, two or more different levels. For example, we want to test 3 different data collection modes. We divide the sample in 3 subsamples, and each subsample is assigned to one of these data collection modes. And we can do this, again, as I already said, according to a complete randomized design, or maybe more efficiently to choose a randomized block design. And again, the purpose is to estimate a finite population parameter observed under the 3 different survey implementations, the 3 different data collection modes. And finally, we want to test hypotheses about the differences between these subsample estimates. And for this purpose, we derive a design-based inference method that accounts for the probability structure of the sample design and the randomization mechanism of the applied experimental design. And the first step to develop such an approach is to define a measurement error model, because we want to test differences of the same finite population parameter that is observed with different survey approaches, survey implementations, or survey treatments, and that require some kind of a measurement error model that explain the difference of the same population parameter that is observed in k different ways. So let y subscript I, q, k denote the observation that is obtained from sampling unit I, that is interviewed by interviewer q and assigned to treatment k. And yeah, we decompose this observation in its true but not observable value for the variable of interest, plus a fixed treatment effect, plus an interviewer effect, and a random measurement error. And the interviewer effect is actually, we allow for mixed interviewer effects, so we can decompose the gamma q in a fixed interviewer effect plus a random interviewer effect, and we have the fixed treatment effects. Yeah, and the model assumptions for this with respect to the measurement error model is that the measurement errors and the random interviewer effects are in expectation equal to 0. We allow for correlated response between the sampling units that are observed by the same interviewer by means of this variance component. We assume that the the measurement errors between different units are uncorrelated, and also the sampling error and the random interviewer effects are uncorrelated. And then our next step is to define the hypothesis that we want to test. So again, the purpose is to test whether one variable, maybe the total amount of unemployment in Mexico, whether these population, I could better talk here about mean, so the average, the unemployment rate, in the final target population, whether if they are observed under the k different treatments, whether they are equal to each other or not. So we construct a vector of k different values for the population mean of interest observed under the k different treatments, and we test the hypothesis. We want to test the hypothesis whether these k-1 possible pairs between these k population means are equal to each other, or whether they are significantly, or at least one of them is significantly different from each other. And we can do that by collecting the population means under the k different treatments in a vector Y, multiply it with a contrast matrix that has the following form. Now, under the measurement error model, you could show that this hypothesis actually boils down to the contrast between the treatment effects in our measurement error model. And yeah, we propose to test this hypothesis with a design-based Waltz test, which is specified here below, where we have a design unbiased estimator for the population values under the k different treatments in y power hat. And we need an expression for the design variance of, I should say, the design covariance matrix for the k-1 contrast between this vector with the k subsample estimates. Oh, sorry. No, I did something mild. And a first step to derive design unbiased estimators for the k population means is to derive the first order inclusion probabilities for the k subsamples. Now, starting with a completely randomized design, conditionally on the realization of the probability sample, we randomly divide the sample in k subsamples. So conditionally on the realization of the total sample, that the probability that the sample unit is assigned to treatment k is just the number of elements that is assigned to treatment k divided by the total sample size. So that is nk over n. And the unconditional first order inclusion probability that an element is included in subsample sk is just the first order inclusion probability of the initial probability sample multiplied by nk over n. Now, for a randomized block design, it's almost similar, but we must realize that we first divide the sample S in B blocks or B homogeneous groups with size NB, and then we apply. Then we do the randomization of the sample units within each block over the k subsamples independently from each other. So the conditional probability that conditionally on the realization of the sample that an element is assigned to treatment k is just the number of elements in block B that are assigned to treatment k over the block size NB. And the unconditional first order inclusion probability of subsample that an element is selected in subsample sk is the first order inclusion probability of the initial probability sample multiplied by the probability that within each block an element is assigned to treatment k, which is nbk over nb. Once we have these first order inclusion probabilities, we can directly construct a general regression estimator for our parameter of interest observed in the treatment k with the sample units that are included in subsample sk. So we just have the Horvitz-Thompson estimator. And if we have some additional information about with auxiliary information for which we know the population totals, we can use that to further improve the precision of the Horvitz-Thompson estimator with this regression adjustment or this calibration adjustment. So in our first step, we now have k approximately design unbiased estimates for our population parameter observed under the k different treatments or k different survey implementations in our experiment. And they are collected in this vector bold y hat. In the next step, we have to also construct or find an expression for the covariance matrix for the k-1 contrasts between the k subsample estimates in this vector y. And as a first step, we have to realize that we have to account for three sources of variation. So we have the variation with respect to the measurement error model, the variation with respect to the sample design, the probability sample design, and the variation with respect to the experimental design. And one way to develop an expression for this covariance matrix is to condition on these three sources of variation as expressed here in the last line. So we can decompose this covariance by the covariance with respect to the measurement error model over the expected value of the sample design and the experimental design, plus the expected value with respect to the measurement error model over the covariance with respect to the sample design, where we first take the expectation with respect to the experimental design, and finally we have also the component that takes the expectation with respect to the measurement error model and the sample and the expectation with respect to the sample design of the covariance with respect to the experimental design. Now, it's a lot of straightforward but tedious algebra, but you can show that these three components can be worked out in the following expressions, where the bold sigma is just the covariance matrix of the measurement errors, and this bold D is just a diagonal matrix for which I will present the expression in the upcoming slides. But first, I want to show if you collect the results, a lot of these components cancel out against each other, and we end up with a relative simple expression where we only left with this diagonal matrix D that is pre and post multiplied with the contrast matrix C. And we can state it implicitly as the expectation with respect to the sample design and the measurement error model. Because it should be understood that once we can construct a design unbiased estimator for the elements in D, then we have by definition a design unbiased estimator for the covariance matrix of the contrast between the k-subsample means. Now, for a randomized block design, it can be shown that these diagonal elements have the following structure or have the following expression, where these AIKs are just the residuals of the regression estimator. And a nice thing is that we actually end up with an unexpected simple expression for this variance structure, because we end up with a variance structure with a variance expression that has the structure as if these k subsamples are drawn independently from each other by means of unequal probability sampling with replacement, where the inclusion probabilities are just the first order inclusion probability of the initial sample divided by the block size. So I call this a simple, relative or a surprising simple variance structure, because no second order inclusion probabilities are involved, although we allow for all kinds of complex probability sample designs. And an estimator for these diagonal elements is given by this expression. And once you realize that a completely randomized block design is just a special case, once you realize that a completely randomized design is just a special case of a randomized block design where you only have one block and where the block size is equal to the total sample and the subsample size in the block is equal to the entire subsample size, then you directly have also an expression for a completely randomized design where you just don't have this summation over these blocks. Let's skip this one. Now, once we collect these estimates for the population means and the estimates for the covariance structure, then we end up with a design-based Wold statistic that has this expression. And if we somehow can prove or conjecture that the contrast between the subsample estimates is normally distributed, then we can also conjecture that this Wold statistic follows a chi-square distribution with k minus 1 degrees of freedom, and that allows us to test our hypothesis. It is relatively straightforward to extend our results. I showed the results for estimated population means, but you can easily extend the results also to to the analysis of the ratio of two population totals or two population means. You can apply the same machinery, and you end up with a slightly more complex variance estimator because you have to adapt it to the variance of the ratio of two subsample estimates. Now, as I said in the beginning, for practical reasons, it might be necessary not to randomize the ultimate sampling units, but randomize clusters of sampling units over the treatments. So we should also consider embedded experiments where we randomize all elements of the same cluster, or all elements that are included in the same primary sampling unit, or all elements that are assigned to the same interviewer, that they are randomized over the treatments. And again, you can apply the same machinery to find expressions for the sample estimates, and also for the covariance of the contrast between the sample subsample estimates. And again, you can do that for completely randomized designs and randomized block designs, and that gives you similar expressions for this Wald statistic. I don't have the time to present them here. It would also become very boring, I think, because it's more of the same. But again and again, the notation becomes a little bit more complex. What we also did is to test statistical properties of this analysis approach by doing very extended simulations. So we constructed artificial populations, and we repeatedly draw probability samples according to different complex sample designs from them. We randomized them over different subsamples according to randomized block designs and completely randomized designs. Add in our simulations all kinds of different types of treatment effects. And we use that to show the approximate unbiasedness of our point and variance estimators that I just presented. And we can also, under this kind of simulation setups, you can calculate the true power of your Wald statistic. And yeah, we illustrate that this is more or less equal to the empirical power that we observe in our simulations. And we also can calculate the expected value of the Wald statistic under all these alternative hypotheses. And we show that this is more or less equal to the mean over the simulated Wald statistics for which we have proposed a design-based estimator. Now, briefly, an extension to factorial experiments. So again, we start with drawing a probability sample S of size n from our target population. And now the purpose is to test the effect of two different factors. So we have a factor A, say 4 different versions of a questionnaire. And we have another factor B, say 3 different versions of data collection modes. And experimental design theory tells us that it is more efficient to combine both factors in one factorial design compared to conducting 2 different single factor experiments independently from each other. And in a factorial design, we combine the levels of factor A with all levels of factor B. So at the end of the day, we have to test K times L different treatment combinations. So we must randomize the units of our probability sample over K times L different subsamples, and which are assigned to these K times L different treatment combinations. So according to a completely randomized design or a randomized block design, we split up the sample in KL subsamples as KL of size NKL. And again, you can apply the same machinery as presented before with an extension of the measurement error model, in the sense that now the treatment effects are decomposed in main effects for factor A and B and interaction effects. And you have to construct a contrast matrix that allows you to test the hypothesis on the main effects for A and B and the interactions. And yeah, I think the details are not important for understanding what's going on. But you can implement this again in our Wald statistic to come up with a design-based Wald test for these 3 different hypotheses. So in this case, you have a Wald statistic to test the main effects for the first factor, where you have a contrast matrix that you plug into this Wald test. And that Wald test would follow a chi-square distribution of k-1 degrees of freedom. You have a similar Wald test for the main effects of the other factor B, which has L-1, where the Wald statistic follows a chi-square distribution with L-1 degrees of freedom, and a similar thing for the interaction effects. It's also relatively straightforward to further extend it to higher order factorial designs to test 3 or 4 or 5 factors in one experiment. You can also imagine, I think, that you can also develop similar expressions to test hypotheses about ratios of two estimated population totals or population means. And of course, you can also construct estimators where for experimental designs where the units are not the ultimate sampling units, but clusters of sampling units. Now, some special cases. You can imagine that under specific conditions, this Wald statistic should be equal to the f-tests, which we know from the analysis of the experimental design theory. Yeah? To be more precise, if you consider probability samples which are self-weighted and experimental designs where the allocation over the treatments is balanced, then in these kind of cases you can show that the Wald statistic is indeed exactly equal to the f-test, which we know from the three-way ANOVAs or two-way ANOVAs, depending on the type of experimental design that you use. And that is indeed the case. And probably that gives a little bit more confidence that these design-based Wald statistics are indeed design unbiased. Even in the case where we only test 2 different levels in one factor, then our results actually reduce to a design-based version of the t-test. And again, if we have a self-weighted sample design, then this t-test can be shown to be equal to the well-known Welch t-test or the standard t-test. Now, coming to an application, finally some data. We did multiple embedded experiments at Statistics Netherlands, and one of them is a mixed mode experiment that we conducted in the Dutch crime victimization survey somewhere in 2013. And at that time, our survey design can be summarized as follows. We had an annual, our crime victimization survey is an annual survey, and the most important publication domains are actually based on the 25 police regions that we had at that time in the Netherlands. And our sample was based on a stratified sample where these 25 police regions were used as the stratification variables. And the allocation of the sample was such that we at least observe a minimum of 750 respondents per domain. And that results in a net response of about 90,000 respondents. And with a response rate, expected response rate of about 65%, this requires a gross sample of 30,500 units. Now, at that time, the data collection was based on a mixed mode design that uses telephone interviewing for the sampling units for which a non-secret landline telephone number was available. And for the remaining respondents, we used face-to-face interviewing. And yeah, inference in this survey is based on the general regression estimator. Now, we did a mixed mode experiment with the purpose to test the effect of a new sequential mixed mode design on the response rates and the target parameters. And this sequential mixed mode design starts with web interviewing. So we write letters to the respondents or to the sample units to invite them to log into our IT system and fill out a questionnaire over the internet. And after about 3 reminders, the remaining non-respondents are followed up by using telephone interviewing if a non-secret landline telephone number was available, or face-to-face interviewing. Now, in this embedded experiment, we had a control group, which was actually the regular crime victimization survey with 30,500 persons, resulting in a net response of about 90,000 respondents. And there was budget to collect data for a treatment group, which is assigned to the sequential mixed mode design, with a size of 3,750 persons, which resulted in a net response of 2,350 respondents. And yeah, since the survey of the sample design of the crime victimization survey is based on a stratified sample design, we decided to use the strata as the block variables in our embedded experiment. Now we focus on 5 key variables, which is the first one is the percentage of people which are satisfied with police performance after having police contact, which is abbreviated as satispoll. Another important variable is the mean perceived amount of irritation of the respondent due to antisocial behavior in the neighborhood of the respondent, which is measured on a 10-point scale. It's called nuances. The third one is the percentage of people that are victim of a property crime. It's called PropVic. We also looked at the percentage of people that are victim of a violent crime, ViolVic. And we looked at the victimization rate of crimes that are reported by the police, REPVIC. Now, in an ideal or a theoretical, according to the theory, you design an experiment where you first formulate the minimum difference that should be observed at the pre-specified significance level and a pre-specified power level, and based on these differences you calculate the minimum required sample size. In practice, it is mostly the available budget that allows us, that determines how large the experimental design can be. And in that case, it is still insightful to do some power calculations to see what you can expect from your experiment. So in the left part of this table, you see what the minimum observable differences are if you test under a 5% significance level, and if you choose a power of 50, 80, or 90%. And if you use the applied design where you have the control group, which is the regular survey of 90,000 respondents, and the treatment group where you have a net response of 2,350 respondents, and then you can see which observations would result in a rejection of your null hypothesis. In the right part, I calculate the minimum observable differences if you would apply a balanced design. So if instead of allocating 90,000 respondents to the regular survey, we equally balance the control group and the treatment group. And then you see a tremendous increase of precision if you would be able to do that. And I just only show you to illustrate that with an embedded experiment, it might look efficient that if you use a regular survey as a control group and you draw an additional probability sample for the treatment group, that sounds sufficient, but this illustrates that you basically combine two competing purposes. According to the purpose of your ongoing survey, you would assign as much as possible sampling units to the regular ongoing survey that is used for your official publication purposes. But according to the experimental design, it's more efficient to choose a balanced design, because that would result into the smallest standard errors for your estimated treatment effects. Now, just some results. In this table, you see for the 5 variables that we tested, you see the point estimates here under the control group with its standard errors, and the point estimates for the treatment group with its standard errors. And because it's a two-treatment experiment, we can now use some kind of a design-based version of the t-statistic. So in the third last column, you see the differences between the control and the treatment group. The t-value and the p-value of this t-statistic. And in this case, you see that only for the variable nuisance, perceived nuisance, that's the only variable where the observed differences is really resulting in a rejection of the null hypothesis. The sample size of the treatment group was actually too small to observe differences for the other four variables, which are basically based on percentages. Now, to wrap up, I illustrate the concept of embedding randomized experiments in probability samples. Again, it has the potential, strong advantage is that it results potentially in experiments that has as well as strong internal validity, because the experimental design guarantees you the causality between the differences in the treatments and the observed treatment effects, but also in a strong external validity, because the probability sample that is used to select your experimental units allows you to use design-based estimators that allows you to generalize the results from a small experiment to a larger extended target population where the probability sample was drawn from. So this is very useful to generalize results to large target populations, which is often important in the case of official statistics. Again, if you use this kind of things to test the effect of implementing a new survey design in an ongoing survey, then it's important that you can quantify the effects, the discontinuities or the effects that this new survey design has on the outcomes of your sample survey. To do that, we proposed a design-based inference method that actually applies to a large set of designs. We did not assume some kind of specific probability sample. We allow for all possible probability samples as long as you can define them by its first and second order inclusion probabilities. And we had a rather broad set of experimental designs that you can use to split this sample in subsamples. Yeah, and again, as I already said, it has many applications in official statistics. And in the past, we implemented these methods in a software tool that is a component of our Blazer suite that we developed at Statistics Netherlands. Okay, that's for it. If you have interest in the details of this approach, that is covered by the papers that you see on this last slide. Thank you for your attention.
Thank you very much, Jan. We have a few questions, and they were written up in the chat, but if people want to make them personally, just raise your hand and make them directly. I don't know if Edmundo Berumen.
Quite some questions.
Well, let me read it. If you have, okay, Edmundo, please. Edmundo, tienes la palabra.
I'm sorry, can you hear me now?
Yes.
Okay, my question is, if you have a repeated survey, like an employment survey that's ready every quarter, what happens if this methodology is used in the sample for a particular quarter and you get valid differences? What if the particular sample in that quarter was not such a good sample? How can I incorporate time to see over time that the difference detected in one particular round are stable in subsequent rounds? That's my question. Thank you.
If I understand you correctly, what you could do is, so you can repeat the experiment in different time periods. So for what I presented so far is that you combine them in one large sample, so that you actually ignore seasonality and that kind of things, and just extend the samples by combining the different time periods in one big experiment. That would basically be the approach if you stay in the context of what I presented yet. Another approach is to combine the results that you observe in this experiment with a time series analysis approach. And there is an upcoming presentation by Paul Smith from Southampton University. He will talk about methods that if you change from an old design to a new design, without having an experiment, for example, how you can analyze differences that comes from this redesign by modeling it with a structural time series model. Well, this approach also has the possibility, if you do it with structural time series models, you don't know nothing about you can model the difference between the old approach and the new approach with some kind of an intervention analysis. Normally, you initialize the Kalman filter with a diffuse initialization, but you can also combine the results of an experimental design within this time series modeling approach, where you use the estimates from your embedded experiments to initialize the intervention variables in your Kalman filter with the estimates that come from this embedded experiment, and then the time series model would also use the information observed for the start of the experiment, and maybe also in the future or after implementing the new design and after stopping the experiment, to further improve the estimative treatment effect of discontinuity. I'm not sure if I'm really answering your question, but
well, we should go to another question by Elias Rodriguez. What details should we consider in the experimental design fieldwork and analysis of the information collected?
Ooh, that you can write a book about this. Designing a field experiment really requires carefully how you organize this in the fieldwork, because most of the interviewers will not be familiar by conducting different versions of a survey under different type of conditions. So if you have, for example, 3 different versions of a questionnaire, you must carefully consider, can an interviewer conduct these 3 different versions simultaneously? Or do you want to avoid that an interviewer have to conduct three different versions of a questionnaire? So then you have to come up with a design that that an interviewer is assigned to one treatment or one questionnaire only. As I said before, you want to avoid too much post hoc analysis. So it's also important in advance to make a clear decision which variables are analyzed, and also specify very clearly which hypotheses are tested. So if you do too much post hoc analysis, that would undermine the overall significance level and the power of your experiment. And again, in the ideal case, you you base the size of your experiment on a decision of the minimum amount of difference or treatment effect that you want to observe under a pre-specified significance level and power level. Yeah, most of the, I don't know how it is in Mexico, but the Netherlands is not that rich. So mostly it's the budget that decides the size of an experiment. But yeah, as I showed, it's still insightful if you have a limited budget to do some power calculations to see what you can expect. And maybe you can, and if that gives you the insight that differences that you can observe are too large, you can maybe find additional budget to increase it, or you can also decide not to do the experiment.
We have another question.
But maybe just wanting to wrap up, that I've won a very early paper in 1996 that is more on design issues of embedded experiments. That might be something to consider. It's the Jos paper from 1996.
Thank you. We have another question from Emmanuel Ben David. He says, in this approach, what does happen if the sample is the whole population? Do the estimates coincide with those of the randomized experiment?
Yeah, if you have, then basically you have K samples that from your population, and then the situation becomes more simple in the sense that you can ignore all the complications from the complex sample design. So in that case, for a complete randomized design, then you basically have K simple random samples without replacement from your target population. That gives you K sample estimates for the population parameter of interest under the K different treatments, but you still have the uncertainty of the subsample size, which is NK. So it's I'm not sure if I understand the last part of the question. Do the estimates coincide with those of the randomized experiments? Yeah, I think the answer is yes. So in that case, you only have to consider the randomization according to the experimental design. And in the case, as I said, in the case of a completely randomized design, it would just be simple random sampling without replacement for each subsample. And in the case of a randomized block design, you would actually have K stratified simple random samples without replacement from your target population. But you still have to deal with the uncertainty of this experimental design.
We have a question from Alfredo Bustos. I don't know if he wants to read it or I'll just go ahead. In your discussion, you introduced mixed interviewer effects in the model.
You skipped one question. Sorry for interrupting, but there was another question for Rodriguez Mones Jose. Right. How many key parameters do you recommend to select to test hypotheses about treatment effects? Yes. That is really, theoretically spoken, an issue of budget. The more hypotheses you test, if you look at simultaneous comparison methods, like Bonferroni tests, the more hypotheses you want to test, actually, the larger the sample size, the required sample sizes to guarantee an overall significance and power level in your experiment. So if there is a budget issue, then you should select the number of parameters as keep them as less as possible. And if you have a lot of budget, it's difficult to say in general it should be 4 or 5. That's not possible. This is really an answer that you have to consider if you do the minimum sample size calculations to and compare it with the available budget. I hope this makes sense.
Okay, thank you. The next questions is Alfredo Bustos. You can read it there. It says in your discussion, you introduce mixed interviewer effects in the models. In other instances, in particular, when, say, municipalities, PSUs are randomly chosen within a state cities, a purely random nested municipality within state effect would seem more appropriate. Could you please comment?
Yeah, I could avoid working with random effect models because I took a design-based perspective. So indeed, I use a measurement error model that also contains random interviewer effects. But if you go through the derivations, I only need that to get rid of interviewer effects in my analysis. But the properties of what we do here, like expectation and variance, that is all related, is all derived with respect to the randomization mechanism of the sample design and the experimental design. But if you want to take a model-based approach to analyze this kind of experiments, then you would indeed end up with random effect models for clusters or primary sampling units or interviewers. But that would be more the approach if you do the analysis from a model-based point of view and using analysis methods from the theory of experimental design theory.
Okay, thank you. We have a couple more questions. The next one is from Emmanuel Ben David. Is there an approach that only depends on sampling design and randomized experiment design?
Probably not that I'm aware of, but I don't claim that I can oversee the entire future. The entire literature. So I have to say I don't know.
Next and last question. Is there a sampling design approach to power hypothesis test calculations?
So. I'm not sure if I understand the question, but if the question is, can you come up with a sample design that increases the precision of your analysis results? Yeah, I think, yeah. Then the answer is each sample strategy that improves the precision of your point estimates helps to increase the precision also of your experimental design. But in this case, it's also the combination that you utilize the structure of your probability sample also in your experimental design. But yeah, if you can, for example, draw in your probability sample your sampling units proportional to the target variables of interest, that will definitely increase also the precision of this kind of experiments. Also, if stratification can result in improving the precision of your sample estimates, that will also help in improving the precision of the experiment. But if you ignore the stratification in your experimental design by applying a complete randomized design, then you destroy this efficiency. So in that case, it would be important to use the strata that you use in your sample design, also to use them as blocks in your experimental design. So otherwise you lose this efficiency gain. But also in this case, I'm not sure whether I'm really answering the question.
Okay, thank you. We're 11 minutes over the time, and another question just came in. Do you want to take it, or should we stop now?
No, I missed the question because I was reading the last question. Sorry, apologies for that. You want me to take the last question?
Yes, if possible.
Yeah, okay. The variance estimation expression from slide 18 looks straightforward. Yes, this is surely useful. Can you please comment on any assumptions and or simplifications that were made? I have to go back to my slides then. Oh yeah. Data.
Maybe you can give a reference.
I'm almost there. Yeah, due to inactivity, I have to log in at Statistics Netherlands platform again. Sorry. So that's what I'm now doing. Yeah, I'm happy that somebody calls this a straightforward result. That is indeed the case. And we did not make any assumptions or ignore any. Actually, the reason that you end up with a straightforward, simple variance structure is that we took into account these three sources of variation. We took into account the variation according to the measurement error model, the sample design, and the experimental design. And that is basically the result that a lot of components that would generate second order inclusion probabilities cancel out against each other. So we end up with some kind of a variance structure that is implicitly defined as the expectation over the sample design and the measurement error model, but it has this diagonal covariance matrix. And if we have an unbiased estimator for these diagonal elements, then we don't have to worry about what happens if we take these expectations. By definition, it will be a design unbiased estimator for the covariance matrix here. And indeed, if you start taking the expectation with respect to the sample design over this expression here, then you will see that you introduce all kind of second order inclusion probabilities depending on the sample design that was used. But you don't have, it's really similar as variance estimation in two-phase sampling. Then these variance structures are also defined implicitly as in expectation over the first phase. That is more or less the same here. So it is actually because we take into account these three different sources of variation that we end up with this relative simple structure. And it is actually the combination of the following factors. First of all, it is because of the assumption that we have under the measurement error model, which is that we assume an additive treatment effect that is equal for all the elements in the population, and that the measurement errors between sampling units are independent, but that is not a strong assumption. An important thing to emphasize is that indeed that we assume a weighting model that meets the condition that we at least use the size of the total population as an auxiliary variable. And in mathematical terms, that is this condition. But that is also not a very strong condition because almost all weighting schemes that we apply contain categorical variables that split the population in subpopulations, but that always meets this condition that you at least use the total population size as an auxiliary variable in your weighting scheme. Another thing that we used is that on top of the probability sample, we put an experimental design, and this experimental design is always simple random sampling without replacement, or stratified simple random sampling without replacement. The first one is the completely randomized design. The second one is the randomized block design. And this overall structure also results in the fact that we get rid of these second order inclusion probabilities. And finally, the most important one is that we use the trick that we directly concentrate on the variance of the contrast between the subsample estimates and not the variance of the subsample estimates themselves. That would heavily complicated the variance estimation procedure.
Okay, thank you, Jan. I think we can stop here. Thank you very much for your very accessible and interesting talk. We had a short course on design of experiments at INEGI, and for other people from outside just before this talk and the ones to follow, I'm sure your results will be very useful for us and other people, and we will be in touch to show you whatever we do in this respect. Thank you very much again, and look to seeing you soon. And I turn the floor to Ricardo.
Thank you. I just want to say thank you to Professor Jan van den Brakel and to you all for participating. Our next conference will be on the March 28th. So please follow the following conferences. There is a link for the small website for these seminars, so you can just register there and follow the conferences. Thank you very much for your attendance. Thank you, Professor Jan van den Brakel, and thank you, Professor de Alba, for your moderation. Thank you to all.
Thank you for inviting me and your interest in my work. And yeah, I would be surely interested to see what you do in Mexico with this kind of experiments. Yeah.
Thank you.
So it would be nice to stay in touch. Yeah.
Thank you very much.
Bye.
Goodbye.
Bye-bye.